Am I in a good spot right here?
You're in a good spot.
Good spot. Morning, everybody, from here in the bunker. Greetings to the Powermetrix Nation. We are having another one of our series of other manufacturers coming on our webinar and giving you some great information about product knowledge, information, specifications, what's going on coming up in the future. And so we've got, it's a very small world. This happens to me all the time, not just because I've traveled so much my whole life, but it's just, I don't know, that's just my life. But actually, one of the guys that's going to be on here today, I knew him from years and years ago when he worked at AEP, Nate Dunn, so it's a small world. I met Nate, met his wife and everything. It's been several years ago now. And so worked with him, and then I didn't even make the connection at first when Joe said it was going to be Nate was going to be involved in this, Nate Dunn, and then he said, hey, I was talking to Nate. Nate said he knows you, and I went, oh, that Nate Dunn. Oh, okay. So so it's pretty cool. So I do know Nate. Know he's a sharp guy, and he's got some great information for you this morning. But as you know, as I always do, before we get cranked up, I'm going to say a quick prayer, and then we'll get rolling. So if you'll join in with me here, I'm going to say a quick prayer. Father, thank you so much for this time today. As we always say, not only to increase our knowledge of our industry and the products, but to do our jobs better, but more importantly, if there's anything today someone can learn to get them home safe to their families, that's what it's really about. So let's get home back to that family safe and sound. So Father, thank you so much for the time today to do that. We lift up all the men and women involved in this industry. If you think about it, it's a sacrificial type of love that we are out there putting our lives on the line to make sure other people that we don't even see or know have electricity and can run their homes properly and run their businesses properly. So so thank you for this time today. Thank you for these men today that are joining in with us. Thank you so much for all of this technology so that we can reach out to folks. And most importantly, thank you so much for what your son did. Without that sacrifice that he made, I can't even pray right now. And so, Father, we want to personify his love, that sacrificial type of love, and love of our, he told us very, very clearly, two greatest commandments: love our neighbor as ourselves, and love your God with all your all your soul, all your heart, and all your mind. So that loving your neighbor these days is getting a little tough, Lord, but by doing so, we show that we are a little different, and we show that we care, and that we do love others. So, Father, thank you so much again for the time today, but more importantly, thank you for Jesus. So all of these things I ask and pray according to the one who paid it all with his life, my brother Jesus Christ. Amen. Cool. Okay, so we'll go through a little bit of our housekeeping that we always do. Today, as I said, go back, man, Godzilla. Jared's pumped up this morning. So we're going to do power quality, power factor, harmonics, and Swell detection. So we will be talking with two experts, Nate Dunn and Joe Childs. Joe, we are very lucky to have as our rep up in the Michigan area, and he's very he's one of the people that Schneider leans on. And as I said, I know Nate from a previous life, so I already know he's sharp, and I do know that my boy Joe's sharp. As you know, he is the Quiz Bowl champ from one of our Quiz Bowls. So I think he doesn't have the trophy right here where you can see it, but he is a Quiz Bowl champ. So so he and Nate are going to be giving us a presentation this morning on all the things that the Schneider meters can do. And also, because you know we don't like to just do death by PowerPoint, as Jared so eloquently puts it, we've got a meter actually here plugged into the training bench, so we'll actually go over some things, and these guys are going to show me. You got to think about this. I don't do that. I'm out there just testing, you know. So I just test the meter, so I don't really know all of the functions and capabilities of these meters. So if they could walk me through it, it's going to be like metering for dummies. So I will go through there and operate the face of the meter and show some things on it. So we will go back and forth. You know how good Jared is. He'll be able to jump back and forth. So we'll go back over here, and we've got a live meter, one of the Schneider meters that we appreciate them sending to us. So we will we'll also take a look at that and look at the functionality of the Schneider. It's a 9S meter we've got here.
So today is metering for dummies?
Wow. Didn't have to go there, man. You did not have to go there. I'm not saying you're not right, but you didn't have to go there. Okay, so the upcoming schedule. So today, as you know, we just talked about it. We've got Nate and Joe. And then on the 16th, we've got Nick Candler with a Durham company. And then March 23rd, JP's taking a little break, and if I ain't got JP, I ain't doing it. So JP's taking a little break for spring break, and then we're going to jump right into some more products. We've got Tri-State, for instance, is looking at, they're already talking to some folks, and so we're going to definitely have some more folks on here from some other manufacturers. So, the folks that we have today, the evolution of revenue meters to smart meters.
That's wrong.
That is. So we've got Nate Dunn. Golly, that's awesome.
That's my fault.
That's awesome, man. Right after you nailed me. I love that. Okay, so, and I won't harp on it. I'm not going to be like Cherry. I'm going to move on. Okay, so we've got Nate Dunn. He's the utility account executive for Schneider Electric. And I'm going to do a little promo real quick. They're lucky to have it. Okay, so Joe Childs, he is president of Electrical Resources Company, and we are lucky to have him. So without further ado, I'm going to turn it over to these two gentlemen, and I will be their guinea pig here in a minute to actually work on the meter. But in the meantime, take it away, boys.
Thanks for the introductions, John.
Sure.
I'll get over to the PowerPoint in a second, so I'll just introduce myself real quick. So I worked at AEP for a little over 12 years, worked in the metering department, more on like the transmission, high-end meters and power plant meters. So I've got a lot of experience with meters, either adjusting their frameworks, working with power quality groups, SCADA groups, specifically with the 8650, which is what we have back there in on the board, as well as like the 7550, 7650 meters. So I'll be talking a little bit today about the functionality of the meters, the different power quality measurements our meters can capture and record, and also some of the importance of meters and just the vast amount of data that's available in electronic meters today. And then, did you want to say anything, Joe, before I open the PowerPoint?
Yep, and my name is Joe Childs. I'm the president of Electrical Resources. I've been the president for a couple of years now. We've been a Schneider Electric rep and a Powermetrix rep for some time. I've been a rep since 2012. So we've been fortunate. Nate's come up to speed, and talking to the Powermetrix guys, they asked if I would like to bring somebody on that we thought that could give some good education on power quality, and I thought Nate has a good presentation. We've been working with a lot of customers here in Michigan and thought it would be a good idea to spread the knowledge further. So thank you very much for the screen time. Nate, I'll let you take over.
All right, thank you. All right, so kind of like the agenda today, we're going to go over some general information on power quality and kind of like breaking it down a little bit. Then we'll go over some like basic power quality and power factor. It's kind of covered in like most revenue meters. Then we'll go into like advanced power quality, which is dealing more with like waveforms, waveform capture, identifying wave shapes, and then how you can use all this information for preventative analytics. So kind of like in the general information, there's like three main categories. You have your meter data, the metadata, and then the event data. So the meter data is getting more into the information about the meter, like the sampling rate is a good example. The ION 8650A, A, B, and C has a sampling rate of 1,024 samples per cycle. Like that's the sampling rate the DSP works at. So that's kind of like the information that is used for like your RMS values. And then when you go into identifying wave shapes, your sampling rate will help identify like what events you can capture. So when you have a 1,024 samples per cycle, you can capture very small events. Where if it's at like say 128 samples per cycle, you might miss a transient because transients can be very short cycle, especially like the ones that only last like microseconds, like oscillatory transients you'll still pick up. But with a lower sampling rate, the peaks will get evened out, so the severity of the event might get minimized. And then the PT and CT settings. So this is kind of like helping the meter identify what your primary values are, other system information, might be like its relative location, like your ITs, if you need like instrument transformer correction, loss compensation. These are all values that go into the meter. They affect your power values. They'll affect like your power factor readings. And then time synchronization and clock accuracy are also like two important information for power quality and revenue. Like if you don't have an accurate clock, like it can drift, and energy being a function of time, like makes your clock accuracy very important. And then when you're looking at your sequence of events, you also want to be able to identify when the meter captured an event relative to like other devices, or make sure that it captured it correctly. And so then
Hey, Nate, I'm sorry. You are no longer sharing your screen. Not sure if you're aware.
Oh, yeah, I was kind of like switching back and forth.
Cool. Just making sure. Thank you.
Because it's mostly just like a few line items.
Gotcha.
So I'll like switch back and forth as we go through.
I knew you was doing
My fault. Okay.
So then when we get into metadata, this is like more information, like where the meter is installed, the type of equipment you're monitoring. So like load types, like it could be like an industrial manufacturer, like if they have like arc furnaces, if they have like large motors, if you're dealing with like distributed or transmission energy resources, you're dealing with different types of inverters, and all these like loads can have different effects on the system. Then you also want to know your meter location and like relevance to your loads. Like most power quality monitors are installed at like the point of interconnection, as that's kind of like your legal agreement point. It's where you want to monitor and capture like harmonic Swell events, not necessarily at the customer load. And then usually if you have a transformer between, say, like the metering point and the customer, the meter may not see as many events as the customer, because transformers can absorb a lot of that, especially if they have other power quality devices in place to help minimize event outages. And then also like your service type, whether it's a Y or a delta. The 9S meter in the back, for example, like is a 4-wire Y meter. Then we also have like the 35S, which is our delta configuration meter. If you use like our panel meters or our switchboard meters, those are software programmable as far as service type, and then we support like delta, 4-wire Y, and like 2.5 element. And then it's also good to know like your customer type, whether it's like a CNI customer, if it's a data center, like what kind of like loads they have. So then when we get into event data, we're usually looking at the waveform, if it's supported by the meter. The waveform can provide a lot of information, not just like the sampling rates, but based on what's recorded, like you can identify the type of event, whether it's like a swell, a transient, if harmonics are an issue, if there was like an interruption. The RMS waveform is more or less like looking at the RMS values over time. It's not like a sinusoidal waveform. But then you also want like the magnitude and duration of events. So the 8650C meter, as an example, has like a swell event log, but not necessarily the waveform capture. And the event log is going to have like your more statistical information. It's going to tell you when the event happened. It's going to tell you how long the event lasted, usually in seconds, and then your min and max values for your voltage. And then just being aware of like your units, whether it's volts, amps, power. So then some general notes before we go into like the more detailed information. Like only like well-practiced individuals are who should be providing your like analysis for event data. This course is just to help everyone be like more informed, be able to like identify like anomalies, like point them out to your like load study specialists or your power quality analysts. So the goal isn't to be an expert at the end of the course, but hopefully you leave knowing a little bit more and gain some insight into what it takes to diagnose an event, how to like understand its impact on the system, and when it comes to power quality, like practice, practice, practice.
Hey, Nate. So what kind of features, if a customer is looking to start recording power quality, start paying attention to this data, what kind of features are they going to be asking for on the meter?
So there's a handful of standards on power quality today. So it's recommended that you use an IEC 61000 4-30 Class A device. So IEC 61000 is like an international standard that deals with main signaling, harmonics, frequency, sag, swell. Like it's kind of like a broad power quality standard. When it comes to harmonics, like a lot of people are using IEEE 519, and it kind of reviews how to measure harmonics, how to calculate harmonics, and then the recommended thresholds for different types of customers based on voltage and load current information. So you're usually looking for a meter that complies with these standards. The reason why like 4-30 Class A is recommended for power quality investigations is 4-30 more or less states that any two devices connected to the same sources will have the same output. A lot of that has to do with how it resynchronizes the sampling rate for the cycles. Like a Class B or a Class S device are more or less going to state that it's going to sample, whatever the sampling rate is divided into your frequency, and it'll give you like a time. So you'll have samples per second, and it just does that in order. With a 4-30 Class A device, it is resynchronizing. I think it's every 3 cycles. It recalculates the period and recalculates your sampling rate to ensure that you are getting 1,024 samples per cycle on every event, not 1,023 or 1,025. And that's how it ensures that the calculation is the same across devices, and then the outputs will be the same as well. And IEC 61000 has a handful of other requirements. There's like 4-7 and 4-15. One of them is in regards to, I think it's like flicker. There's one on specifically for harmonics. There's also some on like sag swell and like voltage fluctuations. So we are looking for a meter that has those requirements. And then you usually want software that is able to collect the data and do some analysis for you. So like our PME software that works with the ion meters, and ion setup has a little bit of these functions as well, allows you to download the waveform. It does like an FFT on the waveform, so you have an idea of what the harmonics are. It'll provide like a phasor view of the diagram as you change your window length on the viewer. And then I don't think it's available today, but like we're also looking at like wave shape identification. So when I go into wave shapes later on, you can identify like if it's a transient, if it's a sag swell based on the wave shape. You can also get a little bit deeper if you know like it's a load and rush from like a motor coming on. If it's like a lot of harmonics generated from like inverters, and trying to take all that information, build like signatures and to help identify different issues. Did you have any other questions, Joe?
Nope. That's what I was looking for, just to give the customers an idea of what they would want to specify when writing that specification to go out to quote, to be able to capture the data that you're going to be talking about today. So that's perfect. I appreciate it.
Thank you. So now we'll go back into the presentation. So we're going to kind of go over like basic power quality now. Kind of like what is power quality. So it was first introduced in like the 1970s, and the term was more of a buzzword in the late 1980s, but it usually refers to the reliability of the electrical system, and it's usually pointing to like voltage reliability, and others refer to power quality as like the characteristics of a power source that allow the equipment to suitably operate. So why does power quality matter? It can lead to decreased productivity. It can lead to wasted product, especially if you lose power in the middle of a production cycle. Depending on what you're manufacturing, like they may have to throw away that entire batch because it's going to get left in the equipment for too long. It's not going to be finalized, and so they essentially have to throw it away, which is a huge loss to the customer. Things like transients and harmonics can also damage equipment over time, and ultimately, it's all about the economic impact to and safety of an operation. So where do power quality problems originate? I assume that a lot of the people on the call today are probably in utilities, and EPRI did a study in the past that shows that consistently about 80% of power quality problems come from the consumer's facility rather than the utility. But they also did a survey at the time to kind of get what customers and utilities perceive power quality events as, which is kind of interesting because utilities, think it's either natural or largely caused by a customer, and the customer's perception is either that it's natural, and then their next biggest chunk is that it's the utility that's at fault. And then, go ahead.
No, that's fun. I wouldn't expect that to be any different than normal. Yeah, the customer's always going to blame the utility.
Yeah.
Yeah,
then,
everybody's trying to point fingers.
Yeah.
And then there are various factors that affect power quality. It can come down to the electrical environment, equipment compatibility, making sure that you have the right rated equipment for your operation, load sensitivity. Something I've noticed more with newer customers when I was at AEP, especially with newer equipment that has computers, it has more nonlinear loads. It's more sensitive to sag-swell events, to where in the past older equipment might have been able to ride through a plus or minus 10% sag or swell, where now the load is more sensitive and small variations can cause them to trip off. And then also infrastructure management. Well, we're looking at reliability, profitability, and productivity. And so this is a study from 2008 to kind of just give you an idea of the estimated cost of downtime per minute. So for a lot of manufacturers, it's about $26,000, $27,000 a minute, and this was in 2008. So that's almost 13 years ago, and these averages have likely gone up. And the mean average was about $35,000 per minute. So that's a lot of money to be down for a day. And I think it came out to 50 million a day. I don't have my calculator on me. But that's a lot of lost revenue. And then when you also think about losing time, you may have to throw away the equipment. If equipment is damaged, it's going to be a lot longer than being down for 12 to 24 hours. So it costs a lot to the customer. And then on the utility side, that's lost revenue, because if your customer isn't up and running, they're not paying their bill. And large industrial customers are most likely your largest revenue points, or they have a much bigger bill than I do sitting at home. And then as we move more into the advanced section, so we'll be talking about sine waves and phasors. So sine waves is looking at the rectangular form over time. So you'll have your real quantities plotted against, we'll calculate it into a real and imaginary number so you can plot it. And then the polar form is what you see on your phasor view. It's kind of I'll usually refer to it as a phasor, and kind of a difference between a phasor and a vector. So a vector doesn't move over time, where a phasor is actually rotating several times a second. But we plot it as a static variable so that we can help understand the representation between VA, BV, and DC, as well as like your currents. So then a little bit about power and inductance. I don't know if anyone ever heard of Eli the Iceman when they were in college or taking electronic courses. But so like Eli is more or less stating that when you have an inductive load, voltage will lead the current. And for Iceman, when you have a capacitive load, current will lead the voltage. So that's something when you're looking at waveforms and you can identify that like the voltage is leading or the current is leading. It also gives you an idea of if you have an inductive load or a capacitive load. If you have a purely like real load, there's absolutely no reactance, then your voltage and current would be in sign or they would be in sync, and you'd have like a unity power factor, which is what I'm going to talk about in the next couple of slides. But usually as your power factor goes down, your demand stays up, but the amount of work being done goes down a little bit. So then the next thing I was going to talk about is the power factor and the impact on utility cost. So when you're looking at like your power triangle, x-axis represents real power or your billable power. I'm not aware of any customers that are built either on volt amps or reactive power. I have seen like some customers at AEP may have had like a kVA like peak demand, more or less ensuring they don't go over like a certain amount of demand every like 30 minutes. And then the hypotenuse represents like the apparent power for the volt amp demand on the system. So for like this example, like I was using, it was like 120 volts, like 3.5 amps secondary, but as like a primary example, 14.4 kV line, like 70 amps primary, and an 86.7% power factor. So in this example, we have about 1.5 megawatts, 873 kVARs, and 1,746 kVA. And kind of like what I'm trying to illustrate is if you have a customer with like a low power factor, you're only billing them for 1,512 like kilowatts, per hour if they're, running consistently. But their demand on the system is actually 1,746. So that's like a couple hundred kilowatts that isn't being billed, but is still a demand on your system. Your generators are having to produce more to deliver the same amount of work. And then this is an analogy that a lot of people usually like. So kind of like the beer analogy for power factor. Reactive power is kind of like the foam in beer. It's wasted or useless. And if you pay by the glass, you want the most for your money. But kind of like looking at this, like the real power is like the actual liquid. But like when you bought for the glass, you're not getting like a full glass of beer. You're getting, in this example, it looks about like 2/3. So on the utility side, this comes down to like your cost to deliver like real power. Customers typically aren't billed for apparent power. They may have like a kVA demand, like peak, but apparent power drives like your generation costs because that's the demand on the system. And then like next we're going to get more into advanced power quality. By advanced power quality, I'm talking more about like waveforms and wave shapes. So we'll talk about different types of wave shapes, like how to identify them, and then some of the effects that different power quality events can have on your equipment and your system. So power quality is usually refers to like voltage quality. Deviations from an ideal voltage are disturbances or phenomena, and these can cause equipment malfunction, they can cause damage, they can cause like the system to shut down or to halt. On the right, we have like several like examples of different waveform variations. The first one is like a short duration in RMS, and then the second example is meant to be like a long duration RMS variations, voltage imbalance, waveform distortion, like noise, frequency variations, and transients. And all of these can be like harmful to your system. Like when you do not have like a reliable source, equipment like will probably like most likely like still run, it's still operational, but there's like the unseen events, like what's going on to like your transformers, causing any effect to any other equipment on your system or the substation. So the term like good power quality can be used to describe a power supply that is always available, always within voltage and frequency tolerances, and has like a pure noise-free sinusoidal wave shape. Poor power quality is sometimes used to describe any supply that deviates from this ideal. Whether or not the deviation is important depends on like the purpose of the installation, the design of the equipment, and the design of the installation. So there are a lot of power quality corrective devices, like there's active and passive equipment. Like active equipment is kind of like a cat bank. When the power factor gets too low, you can throw in a cat bank. It'll bring your power factor up and keep your real power closer to your demand. Passive filters is something like AccuSign that we sell, and it AccuSign actually does like power factor, does harmonics. It can give you some ride through on like voltage variations. The idea is that it's working in real time. It's not waiting for like a set condition and then it activates. As your load changes cycle by cycle, second by second, it is working to ensure that your power is reliable. And then corrective devices can have unique signatures. So this is an example of a camp bank thrown in. A camp bank is kind of like a sinusoidal transient. So it can be like quarter cycle, roughly. And you'll see kind of like in this example how it creates like more or less a sine wave on the sine wave. And then also like analyzing like cat banks. I know they're typically around the 13th harmonic, and then there's usually a couple other harmonics that they inject. But when you like gain this information, it can help you identify what caused the wave shape. Another category is transients. Hopefully you can see these pretty well. The one in the middle is probably the easiest. You can see that it peaked up at the top. A transient is very short term. They can have really high magnitudes, especially like lightning strikes. And the thing you're more or less like concerned with here is you haven't heard of like a lot of customers losing power when transients hit, but it is putting a significant amount of voltage on your system, even if it's only instantaneous. And essentially anything struck by lightning too many times isn't going to fare well too long after. And then this is an example of transients produced by a motor regeneration. You can see that it was running, came down, and tried to come back on. And you can see like the transients or peaks like at the end of the sinusoidal wave shape on the bottom. And then a Fourier transform. So this is what is used to analyze a wave shape and kind of calculate your harmonics. So this example is kind of showing you the yellow line is like your fundamental. So that's your 60 hertz signal. And then they've injected a fifth harmonic, a seventh harmonic to create this distorted waveform. And then the harmonic is a multiple of your fundamental. So we're using like 60 hertz as an example because that's what the US system uses. So like your fundamental will be 60 hertz, your second would be like 120, and then it's showing you the seventh is going to be 420 hertz. And then, so this is kind of an example of low order even harmonics and how they can create a DC offset on your system or inject a DC voltage on your system. And it's usually caused when you have asymmetry between the top and bottom half of your waveform. So for this one, I kind of like used the following harmonics at like the different percentages. And I actually pulled these values from like the typical harmonics generated by an arc furnace or an arc welder, they may not be like the consistent over like one cycle and definitely not over time. But using like the generator I have to create waveforms, this was just like per one cycle. And then some other notes on like harmonics. The even harmonics are usually out of phase with your fundamental, and it's usually between the phases. So I just use like a 60-degree phase shift for reference, but it'll actually be different. Like your odd harmonics aren't going to be in unity. They might vary a little bit, and same with your even harmonics. They're not typically in phase with your fundamental wave shapes. But in this example, you can see how the zero crossing has been offset, and then it's not the same on the top and bottom. And then triplen harmonics are like your third, sixth, ninth, 12th. They're a multiple of 3 of your fundamental. And these have a unique effect in that they sum in the neutral. So if you have a lot of triplen harmonics, you can wind up with current on your neutral or ground, which isn't ideal. And kind of going some differences between like voltage and current distortion. Harmonic distortion of the voltage waveform is normally caused by interaction between the load harmonic currents and the combined impedance of the voltage source at the facility power distribution system. This example specifically is showing a nonlinear load injecting harmonic current into the system, and the system impedance characteristics determine like the level of voltage distortion. And so this is kind of like an example of how digital meters work. So like most meters or all meters today have a digital signal processor that are going to be collecting data from like your analog inputs in real time. And then that digital signal processor is sampling that event at 128, 256, up to like 1024 samples per cycle. And we actually have meters today that are designed specifically for transients that can get up to 150, 167 samples per cycle. And I think there's some that are even higher than that. But what this example is like trying to illustrate is that if you have if the peak and like the rising and falling is in between your samples, the meter won't even notice it. It'll go completely undetected, or it'll get like averaged out. So having like a high sampling rate on your waveform capture is critical for transients, because otherwise you could wind up like missing the event capture.
Nate, what are customers using the high sample rates for these days? If you could give them some examples, like in the renewable world.
So the high sampling rate is usually used for transients. Like cap banks can be captured like pretty well at like 256, 512, because those are more of like an oscillatory transient. So they happen over time. You may not get the true peak, but you will capture the event. Lightning strikes are like an example of the instantaneous transients. I'm trying to think of like some other good examples of like instantaneous transients, but that's usually where you need the really high sampling rate so that it doesn't get averaged out.
What about like wind farm in the solar world?
So like wind farms and solars are fall under like inverter-based resources. So the latest like IEEE standard like is looking at like voltage quality as well as like the harmonics generated by your inverters, and then depending on like I think it's like the number of pulses that the inverter uses, you can identify what kind of inverter they're using. But those harmonics can get injected into the transmission system, and with distributed energy resources, they can be a lot closer to their neighbors, which can affect them if there isn't like corrective equipment in between.
Got it.
And then, so the Nyquist theorem, also dealing with like sampling, is like data must be sampled like more than twice per cycle in order to reproduce it accurately. So like the example on the screen is if we have one sample per cycle, you're going to get a straight line. If you have two samples per cycle, it looks like a triangle wave shape. But the more samples we have, the better representation of the power signal you'll get. All right, so the next couple of tables are going to go over like different wave shapes, an example of the waveform, like their effects and possible causes, as well as like possible solutions. So we talked about transients, impulsive and oscillatory. So they can cause loss of data, possible damage, as well as like halting the system. For impulsive, like this can be like lighting, switching impulses, utility fault clearing. Possible causes for oscillatory trances is usually like switching of inductive or capacitive loads. So when you're like switching the cant bank, you're switching it out. And then like different solutions can be like a universal power supply, zero crossing switch, as well as like reactors and chokes. So an interruption, so this is usually when like something causes like the voltage, like a fault happens, voltage is lost for a period of time. So this can cause a loss of data, damage or shutdown. Possible causes can be from like switching, utility faults, circuit breaker tripping, or component failures. The recommended solution is like a universal power supply. For like sag and under voltage, as well as like swells, they can, well, I think like system halts, loss of data, and shutdown is common between most of them. So for like sags, like startup loads can cause a sag and faults, as well as like load changes. And then having like a power conditioner or UPS gives you like the ride-through capability when you have like a sag or under voltage event. And then like swells can be caused from like nuisance tripping, either like damaged equipment not operating correctly. And possible causes can be from like load changes and utility faults. And then like similarly having like a power conditioner, universal power supply, or ferro-resonant control transformers.
So Nate, the relationship between, you can go back,
Mm-hmm.
the relationship between sag under voltage and swell over voltage, is one more extreme than the other because they're paired together there?
Yeah, so like a sag and a swell is a short duration, like maybe several cycles. But usually if it lasts like seconds or longer, then it'll fall under voltage. And an under voltage is like lasts not indefinitely, but it lasts for a much longer period of time.
Gotcha.
Where a sag and swell, so I think like most people might be aware of like the Sedema curve. It's kind of a way to plot sag swell events as and how like what your ride-through capability would be. And so with like a sag or swell, like usually you can handle like a short drop for so many cycles. But when it's indefinite, that's when you get like an under voltage or over voltage.
Gotcha.
And that's usually when equipment is definitely going to shut off. Where with a sag and swell, might be like noticeable, but you might be able to like ride through the event.
Gotcha. Thanks.
And hey, Nate, Virgil Johnson wants to know, there seems to always be a certain amount of transients we measure. So at what point should we be worried about the transient?
I think when you're like looking at transients, probably like frequency, especially if your transient voltages are exceeding like your voltage ratings, like you're hitting your equipment with a lot of voltage, and if it's happening all the time, like you're going to reduce the life of that equipment. And then also identifying like where the cause is coming from. Like if you're seeing oscillatory transients all the time, it could be like a cap bank that's operating more often than it should. And then like trying to understand why is it operating so often? Is it like the customer's like load? Are they like bringing on something that's constantly causing the power factor to drop a lot and having to like switch on? And I haven't usually seen like the cat bank transients as they don't have as large of a peak as say like a lightning strike. But if they are exceeding like your voltage ratings, that is ultimately causing like damage to your equipment, especially if it's frequent and over time. And how much time do I have, John?
Got about 10 minutes left.
10 minutes left.
All right. So I'll probably like finish up on the wave shapes because I wanted to get into the meter a little bit. And as he's like going through the meter, like just talking about like all the information that's available in meters today, and how to like take advantage of that information and use it. So these are just like some different waveform disturbances like DC offset, harmonics, inner harmonics, noise, voltage fluctuations. And then there's a couple of things on like signatures. So like wave shapes can have like unique signatures, and you can kind of like build a database, or like over time you'll kind of like be able to recognize transients, sag swells, and then also further like differentiate what kind of load could be causing it. And same with harmonics, like a lot of devices like inverters, VFDs, ARC devices typically generate like the same harmonics, so that can help you identify what's causing them. And then now might be a good time to switch over to the meter, because I'm going to more talk about kind of like a history of the meter, and just like all the information that's available today. So kind of like a brief history of meters. Like they used to all be electromechanical. Some meters had like no output at all. You might have had like a KYZ, maybe 2 KYZs. That's also, if anyone's familiar with like Q meters. A Q meter was used to like simplify reactive load measurements, because you could use a kilowatt hour meter with a, I think it was like a 60-degree phase former to get Q, and then that would be for the delivered real power quadrant, where var hours delivered and received requires like a 90-degree phase former on electromechanical meter to capture your vars. So then we went into like electronic meters, which brought additional I/O, and some of them had serial communications. And then today's meters support like 4 quadrant measurements in a single device. You know, they still have like legacy support for I/O. You can have multiple simultaneous data connections to more than like one data master at a time. Pretty much every register in the meter can be mapped to like a Modbus DMP output. A lot of devices support 60 and 850 as well now. They can store wave shapes on board the meter. They can be supported like natively in their protocol, or they can go into like ComTrade. And then some protocols support higher update rates. So like Modbus in the meter is like 1 second. And I think our DMP registers update up to 8 times per second now. So now kind of like going on to the front of the meter, if you can hit the Alt-Enter button, John.
Yep.
So this will put us into the alternate screen. So the alternate screen has a lot of the additional pages. So like right now it's on the phasor view. So this gives us our voltage and current relationship. And then usually if you see like the current is leading or lagging the voltage, like that is an indication that your power factor is low. There's also like voltage trends, and your harmonic display is in the alternate mode. So the alternate or the harmonics display goes up to like the 63rd, and it's just using like the 1 second average. It's not using the like 1024 samples per cycle like waveforms to calculate your harmonics on that page. But just to get a quick overview of like your lower order harmonics.
One more quick question. MBDA asks, power quality monitors have to be calibrated yearly. How does this apply to the Schneider meters?
That would be the same. Any device that you're using for billing or regulatory, I believe requires annual testing. So like having like a test kit that can inject harmonics and then being able to like see its impact can be like critical when you're testing these types of devices. And then kind of like with all this information, Like, what can we do with it? So like Power Monitor Expert is another software from Schneider, and this one has more of the advanced analytics built into it and reports. Ion Setup, you can like see the data recorder, but it doesn't really do any data analysis for you. But you can use like data recorders for historical analysts that can be helped like develop like your nominal or typical like load curves, like operation. PME can like natively read the waveforms from the ion meters. And the ion meters store waveforms like in their native ion protocol, as well as like ComTrade. If you download it as ComTrade, then you can use something like PQ View or PQ Diffractor, some other applications to view the ComTrade file and analyze it. And then with PME, you can also organize your alarms by like severity and type. So that's like a new feature. I think it was introduced in like PME 9.0, where you can kind of like categorize the alarms instead of like just seeing like a huge list of all the alarms. It helps like filter them out for you. And it also supports like different reports. Like our meters support like there's a 4-30 report. It's kind of like a general PQ report. It's looking at like voltage, frequency, your THD values, and has like some Swell events recorded in there. And then we have like a 519 report that's specifically looking at harmonics and is making sure that they're not exceeding the recommended thresholds per the 519 standard. And then there's also like a EN 5160 report that's supporting our meters. And that's like a European report, so I haven't seen a lot of US customers use it, but it's available. And then with PME, you can also create like custom, dashboards to kind of provide like an analysis of your events, of your loads. If you're seeing like abnormal harmonics, you can build a page to like notify you of that information. And then
Nate, so a lot of our revenue customers, they're used to capturing this data every 15 minutes, 4 times an hour. What do you recommend if a customer is going to go out and specify the Ion 8650A meter to capture all the power quality data they can? What do you recommend? How often would you recommend capturing this data?
So with like a lot of power quality standards, they kind of specify the time for you. Like 519, your harmonics need to be sampled at 200 milliseconds and then aggregated every 3 seconds and every 10 minutes. So we have like a recorder set up in the framework to record the 10-minute data every 10 minutes. And the 3-second data could be made available if you wanted to like customize the framework. Flickr has like a 10-minute and 2-hour standard definition. It's like PST and PLT, which is like your long-term and short-term flicker measurements. And in the Ion, the instantaneous flicker measurements aren't like stored in a data recorder, just the 10-minute and 2-hour values are. And it seems like 10 minutes and 2 hours seems to be what a lot of the standards specify.
One more question
Gotcha.
from Mike P. How do you protect against loads that cause zero crossing transients?
Well, I guess to be like honest, that one's a little bit beyond my expertise. But I can, I'll take a note of it, and I can like get that information back to like John and Jarrett to
Great.
share with you guys.
No problem. Thank you.
Yep. Then like something I kind of wanted to like end with like kind of like the benefit of power quality monitoring, like understanding what's happening on your system. So I think EPRI did a study in 2014 that the average power customer will experience approximately 50 sags a year that can result in a system shutdown. So if we looked at like that mean cost per minute across the industry, it was like $35,000 in 2008. Like that comes down to like 40.4 million a day on average 13 years ago. So that value's like likely gone up. And that's for like an outage that lasted a day. If it lasted 12 hours would be like half of that, but if it lasted like a week, that'd be a huge shutdown. And then fault location analysis. So I didn't really have time to talk on like the disturbance direction detection in our meters, but knowing like the direction of the fault, and then there is like equipment that can do like a calculation of distance to fault. Like being able to calculate where the fault is can reduce like your time to locate it in half. Having like just the information available to help you like find it instead of having to send people all over the system to like manually inspect. And then wave shape analysis can help determine like load and trouble equipment causing disturbances on your system, so you can identify what needs to fix instead of like having to rebuild like the whole station just because you've had issues. Harmonic analysis can help further determine the load and like other corrective measures that you can take to minimize impact. And then historic analysis can be used as like a baseline. So like with PME, I know a lot of people use Pi. It gives you like a trend over time, and depending on how long you store, that information. If you start seeing anomalies, you can like look back in time, like have they always been present? Is it something that started happening recently? Like you can do some like statistical analysis to identify if like something changed in your equipment, like at a specific date if you started seeing those events. And then just like some key points to remember, like power quality is like a set of limits that define like how equipment and electrical systems can operate correctly. Many power quality standards exist in different parts of the world to assist in the identification of electrical disturbances. And advanced power logic devices like our ION are able to capture waveforms and events when power quality disturbances occur. And then just knowing as much as you can about meter data, metadata, and actual event data to help analyze it. And then Power Monitoring Expert can be a useful tool in analyzing these disturbances and like various components of the software. And then here's like a few articles that I've read that help put this presentation together, as well as giving you like information on different power quality disturbances, like how to analyze them, and additional information about them.
Good deal. Well, thank you, fellas. We really appreciate it. A lot of knowledge there. We appreciate also the making the stuff available to you with the references there. I'm sure if anybody would want copies of the presentations, they can also contact us for that, and we'll definitely get back on that the zero crossing question that came in. I know I was just up in Kentucky last week. I can't imagine all those distilleries for Buffalo Trace if something went down on them and they had to start throwing out batches of all that bourbon that was in mid-fermentation or something. So that'd be catastrophic for that part of the world, and for everywhere for that matter. If nobody could get any Pappy Van Winkle, it would be really, that might cause an uproar in the companies, in the country. So, so anyway, thanks so much for all that. We really appreciate the time. We appreciate sending the meter down so we could actually look at one in action. And we just appreciate all the folks that tuned in. And as you said, if you got any questions, holler at us. We will give a follow-up back to that one question. But everybody be safe out there and be careful. God bless y'all. Thanks a lot. Thanks, fellas.
Yep. Thank you. Good time today.
We'll see you.